When a viral button claims to instantly fix Amazon search, it feels like magic. But for developers building AI features, this isn't about a trick. It is a lesson in architecture that solves the latency and cost trade-offs you face daily. Today, we connect that headline to the engineering reality of retrieval, augmented generation versus raw API calls, showing why local filtering often beats massive models at scale. The viral tool works because it acts as a specialized pipeline, not just an AI call. The magic is actually architecture, specifically how systems handle data before sending requests to expensive servers. Consider the Chrome extension that filters out pseudo-brands by detecting unpronounceable consonant runs in product names like SZHLUX. This logic executes entirely within your browser as a local script. It uses allow lists and heuristics to block junk instantly, without ever querying an external server for every single item check. This mirrors the critical decision developers make when building AI search features. Why send a request to a slow, expensive cloud model when simple rules can handle 90% of the filtering? The extension avoids network round trips, drastically reducing latency and cost compared to sending raw product data through an external API or a large language model for basic pattern matching. However, many engineers assume that adding any AI capability automatically solves complex retrieval problems. They are wrong without proper architecture like vectorization and inference optimization. If you just call an LLM on unstructured search results, you often get expensive hallucinations instead of accurate answers. A study analyzing multimodal large language models attempting to filter Amazon search result pages found a startling failure rate for standard prompting techniques. The research showed that raw AI attempts achieved an F1 score of only 0.21 when trying to identify relevant products versus junk. This number is shockingly low, proving that the model prioritized visual clutter like badge importance over actual content relevance because it lacked specific architectural context. It simply could not distinguish quality without structural constraints or human-like reasoning patterns built into its workflow. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Even when researchers applied diagnostic prompting, forcing the model to explain its reasoning step by step, the score jumped 858%, reaching a new high of 0.297. Yet even with this massive improvement, absolute agreement with human experts remained low at a Cohen's kappa of just 0.071. This proves that raw AI is insufficient for complex retrieval tasks without structural constraints and specific data context to guide the decision-making process. To beat Amazon search or build your own reliable system, you need retrieval augmented generation. This approach involves converting product descriptions into high-dimensional vectors to find semantic similarity rather than relying on simple keyword matches. The viral button works because it functions as a RAG pipeline. It retrieves specific data like block lists, augments the user's view with that context, and generates filtered results without needing to reprocess the entire Amazon catalog in real time via an LLM. The lesson here is about prioritizing your system design trade-offs. A small, well-architected system often outperforms a massive, unoptimized one when latency matters most. You must ask yourself if you need an AI for every single query, or if a simple rule-based filter can solve 80% of the problem faster and cheaper. This applies directly to designing RAG systems where retrieval efficiency dictates the entire user experience. When building search features, prioritize data structure like vectors and embeddings over model size alone. The original Amazon Dash button serves as historical context for this lesson on automation triggers. While that hardware is now obsolete due to server-side bricks, the open-source community repurposed it into local IoT triggers using ARP packets. This reinforces the engineering principle that local control often beats centralized dependency when reliability and speed are paramount. This distinction between local logic and global resources defines the difference between a junior engineer who calls an API for everything and a senior architect who understands system boundaries. The viral button teaches us to trigger local logic before querying global resources, ensuring we do not overload our infrastructure with tasks that can be handled closer to the edge or within the client itself. The Max Planck Institute's study on algorithmic auditing further highlights how detecting self-preferencing requires scalable tools rather than just human intuition. You cannot rely solely on a model's output. You need empirical validation and structured data pipelines to ensure your system behaves as intended at scale. This is where the real engineering value lies, in building systems that are robust, efficient, and cost-effective for production environments. Understanding how to implement local filtering or heuristic pre-processing before hitting the model separates career growth from stagnation. It forces you to think about the full data flow rather than just the immediate output of a black box API call. By focusing on these architectural details, you build systems that are not only smarter but also more reliable and cheaper to run in the real world. The takeaway is clear: do not default to calling an LLM for every query when simple logic might suffice. The viral button works because it leverages a specialized RAG pattern with local filtering capabilities rather than brute force computation. This approach minimizes latency, reduces costs, and delivers results that feel instantaneous to the user while maintaining high accuracy through structured data retrieval. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.